be directed perpendicular, net field inside the container due to static charges 0. All these ideas you are going to help in. The 2 chapters revolve around these small basic ideas. Just core fundamental ideas is what we are going to use in the coming chapters. Okay, now earthing of shells. So electric potential of earth is 0. We know conductor is an equipotential. Will I agree? Let me give a general first description. So there's a body is there. There's a body. No. There's iron made up of iron. This one. Now what I do is like there's a wire. And it will be connected to earth. So I have so to make you imagination, I'm bringing this all this is a earth. We know what is the potential of earth is in fact 0. The potential of earth, we take it to be 0. Now that the iron body is there, so it's a conductor. No, iron is a conductor. Now the earth is what is the reference for us. It's like a sink, electric sink you can call it. It's having a 0 potential. So potential of earth is how much will be 0. Whether you add charge or take out charge, it's like infinite sink, like in thermodynamics, how we had a sink. No, similarly, what happened in like a electrostatic, this will be like a sink, you can say, like you add any amount of charge to it or you take out any amount of charge, what happened to potential of the earth will remain 0. Potential of earth will be 0 when some charge gets added up, because what is the capacity of this will be infinite. Am I right? Okay, there's a conducting wire. Copper wire, I'll write it. No, what is the potential of this? Potential of earth, I'll write it ground. So what is the potential? So this will be 0. Now there's an iron body. So let's assume that it's having some potential. Then copper is also a conductor. No, so when I join, so this is very important. There's a point A, there's a point G for us. No, there's a copper wire. No, so when I close this, this copper is also a conductor. Then potential conductor is equipotential. So then what this wire will do will make potential of this iron body equal to that of the earth. The reason for that, this wire is a conductor and conductor is an equipotential surface. Getting the idea? Getting the idea now? So how to make potential of this iron body equal to 0? Just connect a copper wire between that iron body and the earth. Then potential of that will become 0. Conductor is an equipotential. On closing switch, potential of A will become equal to G. Potential of the ground is how much, or earth, it is 0. So therefore, potential of the body also will become 0. So when I close this switch, potential A equal to G and potential of G is 0. So therefore, what is the potential of A will also become 0. Okay, fine now. So any body, any conducting body, if it is earthed means by using a conducting wire, I'll connect it to the ground. The ground is what we say, no? So it's called like a grounded or earthed. This symbol is used for earthing. Instead of drawing the earth symbol R, no, we just show by this. It is assumed that it is earthed. All of you got the idea? This one? Okay, let's sum that one. So what is the conclusion now? When any conducting body earthed, potential of that will become 0. When a conducting body earthed, its potential becomes 0. Okay, similarly, that earthing is what we are going to do here now. Okay, now he's asking, after earthing, the shell A and B are given charges Q and 3Q. After earthing, I'm asking what will be the charge on each surface. Then what is the potential of the shell which is not earthed? Find the charge on each shell and potential of shell A, which is not earthed. Okay, now what is the method? Here, I don't know what happened final charges after earthing. The switch is closed, so conducting wire, you better write. Switch, anything that it be. Okay, now what is the charge here? Let the charge here be Q1. We don't know what are the charges. Then here charge Q2 and final charge Q3. And then what we are going to do is like we are going to take help of. Again, a small procedure is there. Follow that procedure. It'll be very easy for you. So this is the inner shell. The outer shell. Where is the pink color? Oh. It's in fact thin. All the shells are thin, but what I do is like to make you understand, I'm making thick here, that one. This is R. This is 3R. Now what I do is I'll ask you to assume a Gaussian surface in the material of shell B. Now what are the charges we give? So this will be, this for the charge Q1, Q2, Q3. No, where is a, there's a shell A, there's a shell B. What will be the net field at point P? Net electric field at point P, because the point P lies inside the conductor. We know Gauss law conditions, conductors. The net field inside the conductor due to static charges must be 0. So therefore this EP must be 0. If EP 0, then flux should be 0. Net flux 0, net charge enclosed 0. So therefore Q1 plus Q2 equals 0. This is the equation 1. Everywhere you can use, not only this problem, everywhere. No, a shell which is not earthed, the charge of the shell should be conserved. No, we'll apply conservation of charge principle. Which shell is not earthed? Shell B is not earthed, so charge of shell B should be conserved. So what is the next idea? The charge of shell B is conserved because there's a reason it is not earthed. What was the charge of shell B? 3Q. So therefore 3Q should be equal to Q2 plus Q3. Equation 2, I got it. How many unknowns are there? Q1, Q2, and Q3. 3 unknowns are there. I have 2 equations. I need one more equation. So a shell which is earthed, what should be the potential of it? Which is, oh, so wait. Shell B is earthed, no? Charge of shell A is conserved, sorry. Charge of shell A is conserved. What was the charge given to shell A? Q. So therefore, from 1 to what we can write it? Q2 equal to minus Q. So what all the charges we got it? Please notice shell B is earthed, no? Shell A is not earthed. So charge of a shell which is not a charge of shell A is conserved because not earthed. What was the earlier charge given? Q. No, the charge will remain same as it is, Q1. Then from this equation 192, Q2 equal to minus Q. So what is the charge here? Q minus Q. We have to calculate this charge. Now, a shell which is earthed, what should be the potential? When a conducting body is earthed, its potential becomes 0. So shall I write expression for potential B 0? Then I'll write equation potential B should be equal to 0. Why should be 0? Because shell B is earthed. Okay, let's write equation. Okay, this thing. No? What is the potential of shell B? Can we write it? Again, the superposition principle. First, KQ1 3R, KQ2 3R, KQ3 3R. Just now you all learned it. So we know Q1 plus Q2 0. So solving this, Q3 will become 0. What is the potential of shell B? KQ1 3R, KQ2 3R, KQ3 3R. Q1 plus Q2 is in fact 0. So finally we'll get Q3 0. Means there won't be final charge here. Now what will be the system? How do it appear? The whole system, how do it appear again? What are the final charges? This will be Q minus Q. This will be 0. This will be your final system. Okay, now looking at this, I am asking you to write the potential of shell A. A shell which is not earthed, its potential should be determined. I think, okay, you are able to see. Yeah. How to write potential of shell A? K Q by R plus K minus Q by 3R. 2KQ by 3R.
Sir,
Ama.
but potential at B will be 0 now, sir.
Yeah, okay, I wrote 0, no.
No, sir. So that only potential at A should be only KQ by R now, sir.
Superposition principle, ma, when you're calculating potential at shell A, looking at this diagram, KQ by R minus KQ by 3R. I know potential of shell B is 0, no doubt. But when you're calculating potential, potential is at a given point will be due to charge on all surfaces, whether you earth a shell or you don't earth a shell. Huh? Okay, I think I'm giving complete description of problem, see once. All these are not concept, just method. 1 or 2, 3 problems, if you understand, you can manage very easily.